Okay. Oh, no, I can't stand right there. I swore that light follows me. Okay. Welcome, everybody. You have found your way to the July edition of our University of Lowbrow Astronomers meetings. A lot of us consider actually this maybe is our favorite meeting of the entire year. We get to come over to beautiful Eastern Michigan University's campus. We get to enjoy all kinds of Norb's toys, I mean tools and educational equipment that's over here. And as you'll discover if you haven't seen it before, he's got to be one of the most brilliant people in astronomy you can imagine. And he doesn't have to pay for it. In fact, they pay him. It's amazing. Anyway, I'm Charlie Nielsen, the president of the club. We do have a couple of other officers, a few here, and we'll get some brief reports on them later. But as tradition would have it, we always have our guest speakers speak first. Tonight, that is Miles Mercier. Also, we're going to have a little, I said in my meeting announcement that I sent out that we have a little surprise coming up. And that's going to be a little short thing by Norb, Dr. Pat Seitzer, and one of our vice presidents, Brian Ottum, who recently took a trip down to Chile, where we have the U of M and big telescope down there, biggest round thing, and they're going to give us a little thing about what that trip was like. And then after that, we'll try to get through the officers part, then have some more fun because we're going to walk over to Sherzer Observatory, and we're really lucky. It's a clear night out there, and we'll get to enjoy all these toys, I mean tools that Norb has over there. So anyway, with that, Miles Mercier is a recent graduate of Eastern Michigan University. How convenient. Which coincidentally is where we are right now. He graduated this past April with a bachelor's degree in physics and a minor in astronomy. Miles plans to continue his education and obtain a PhD in astronomy, where he will continue to learn more about radio telescopes in the early universe. He was president of the EMU Astronomy Club for 2 years, and because of his experience running public events and presentations, Miles obtained the role as a NASA Solar System Ambassador based out of Westland, Michigan. Miles has been interested in radio astronomy for about 1.5 years now. He'll be talking about his personal experience with radio astronomy, which was an independent study during his time here at EMU, and his article and research paper about detecting hydrogen in the early universe. His talk title is appropriately Radio Astronomy in the Early Universe. And with that, please welcome Miles Mercier.
Okay. Well, it's been a little bit since I've done a public talk, so don't judge me too much. Oh, great. Okay. Now the research paper I'm talking isn't my own. I don't know if I heard that correctly. It's one that I found online and talks about interest that I want to continue my education and all that. I wish I was a part of that paper, but I was 17 at the time. So if that would have been great.
Well, that's right.
Well, all right. So, yeah. All your toys.
Yeah. Bear with me. Bear with me. Yep.
Okay. So, as Charlie said, radio astronomy in the early universe. Tonight we'll talk about radio waves. We're going to do like a little brief introduction about radio astronomy for those who don't know about radio astronomy. I know Peach Mountain has an old radio telescope on the hill, but for new members and all of that who don't know too much about radio astronomy, we'll talk about radio waves, how radio telescopes work, the hydrogen line, which is one of the most important frequencies for radio astronomy, my personal experience with radio astronomy, and the observations of the universe from MIT and Arizona State University. So with that, we'll move on to radio waves. So radio waves range from 3 kilohertz to 3 terahertz, which is the largest portion of the electromagnetic spectrum, which means there's a lot of things that we can do with the radio spectrum. And what we can do, there are natural and man-made frequencies that we use. We all know AM, FM radios, we listen to music, we listen to the news on NPR. And we also coordinate around the world with planes, boats, and from that, we can also communicate with spacecraft too. We use radio waves to communicate with spacecraft. And we can tell them commands, receive data from that. And from some of the objects that we can see in the radio spectrum are galaxies. We can see, Cast A. You can see the center of our galaxy, Sagittarius A. And we can also look at the sun. We can look at activity in the sun. And we can also look at the ionosphere of Jupiter, where we can see storms from as well. And we can see a lot more. So how radio telescopes typically work, this is a parabolic dish here. So you have the radio waves coming in that go up to subreflector, that go to the secondary reflector that then goes to the feed horn, then travels down to the amplifier, which is what tunes the antenna at that frequency. And then it travels again to another cord, to a computer or data bank storage, and where we can look at the data and manipulate it and see what we get from it. And so here we have just a portion of the night sky here. This is what you can see with an average telescope, an optical telescope. It's pointed at some random part in Aquila, but with a radio telescope, it's actually called the Manatee Nebula. Yeah, W50. And so it's clouds from a nearby star next to a black hole. And all that is the black hole just taking away the particles and all of that from the nearby star. You can't see that with the naked eye or with the optical telescope, but with the right frequency and a large enough dish, you could see that. That was taken from the Very Large Array down in New Mexico, the VLA. So we'll move on to hydrogen. So we all know hydrogen is the most abundant source in the universe. It comprises about 73% of the universe, while the other is 25% helium, and the 2% is all the other elements that we know. And so hydrogen allows us to look further into our own galaxy, and as well as beyond that. We can get compositions of distant galaxies as well as our own. We can map out and look at the densities and stars and nebulae around them as well. And so this magical frequency is called the 21 centimeter line, which is 1420.405. There's more numbers along that line too. Those numbers can be important if you do close proximity radio astronomy. But anyways, how it occurs is when radiation is emitted or a photon is emitted from electrons transitioning from the first excited state to the ground state, and where in that process the electron will flip in relative to the photon in the center. And so the 21 centimeter line is very important as it can pass through interstellar dust that blocks optical telescopes, and where we can dive deep into our galactic center and allows us to understand our own galaxy, and then beyond that, our the universe. And so here's my radio astronomy adventure. There I am. This is taken in March, and there's a little radio telescope that I built here at EMU for my advanced study. I learned from the Society of Amateur Radio Astronomers, I forgot an A in there, or Sarah, from their website, a member that came to speak at EMU's Astronomy Club. They gave me a presentation about radio astronomy. And from that, I was able to kind of pick and gather information on radio astronomy. I was very, very deeply interested by it, and I wanted to try and get some experience with it while I was in my undergraduate. And so the scope itself is made for a zenith pointing scope. That's what the directions they gave. I went down to our machine shop and we fabricated a dovetail just by drilling some holes, and we were able to attach it to an equatorial head where I can really move it in any direction that I want, rather than just waiting for an object to pass over. I thought that was kind of boring. I wanted to look at other things rather than just wait. I'm impatient. And so I was curious, and so I was amazed that I could take it out during the day and get data. You know, with an optical telescope, we can't. I mean, we can do that, but it's kind of hard to do that. Where a radio telescope, you type in the frequency on the software that you're using, and lo and behold, you kind of aimed in that direction based on the aperture of the radioscope, and you can get data. So I took data of Orion, about 10 degrees of Orion at night, and then in the daytime, because I took data on Cygnus. And I was able to get the data. I got the data, and I was able to write a Python script to kind of sift through the data, plot it, and from that, look at the redshift based on the observed frequency versus the emitted frequency, that 1420.405 megahertz. And from that, calculate the relative velocity from the portion I was looking at to our position with now. So I have my example from Orion right here. You can see a very distinct peak. That's very important. If you have a distinct peak, either up or down, that means you've picked up something. And so you can take longer data sets and kind of clean it up. This is about 9,000 iterations. I just kind of held the telescope up with the mount. Just took time and was able to get a clean, beautiful peak. There weren't any RFIs or interference or interference. I took this on top of Sherzer, surprisingly, 4 stories up. Car horns underneath it, but it wasn't affecting it that much. And so here I have kind of written with the plot. I was able to program with it. It has the peak frequency here, which doesn't match the 1420.405. It's actually a little smaller. So you take your basic redshift formula right there for frequency, and you do the emit minus the observation divided by the observed frequency. And depending on if it's greater than 0, it's a redshift. If it's less than 0, it's a blue shift. And we can see the peak frequency here, plugged in those numbers on 1420 and all that. And we get a Z factor of that's positive, so we know it's a redshift, but it's very small, which means that the redshift isn't too great. It's not that far away from us, which kind of makes sense here. Orion isn't that far; it's right in the back door for us. And I calculated the velocity right there. The bottom equation there is to make the conversion rather from meters per second. That's velocity. I have converted it into kilometers per hour, so that 3.6 is just for the conversion factor to make it more understanding with cars. I mean, besides America, kilometers per hour is the standard, so I try to keep it in standard units for that. And so that kind of correlates. It's redshifting. It's farther from the galactic center, which correlates with it. And then moving to Cygnus, a little noisy. All right, so here we can see that compared to Orion, it's a little more noisy. I took this in the pier. There were trees around and telescope motors moving around, which caused interference. Keep going with that. And so it's a little messy, but it still has a distinct peak right here. So 1420.272, which plugging into my Python program gave us a negative value, which is the value of -2, so it's shifted, and with a negative velocity of 50,000 kilometers per hour, which is very fast, mind you, and the stars are moving very quickly. And so that's my personal adventure for radio astronomy. I could do more from that. I plan to alter the code and kind of try and get a tangent method, which is to calculate the distance from the galactic center and our location to that object where that we're observing. But now for my main thing, that was just a little background to kind of show I know what I'm talking about a little bit. I'm still an amateur with that. But in 2018, astronomers detected the earliest evidence of hydrogen in the universe. And that right there, about the size of a table, this table that's in the middle is about the size of that. and then it's got a 150 foot by 150 foot mesh ground plane right underneath it. It's ginormous, and it's in the middle of nowhere in Western Australia because there's barely any interference there. And so this project is it's from EDGES, or the Detect Global Organization, which signature. And so from that, they got funding from the National Science Foundation to see if they can pick up early hydrogen in the early universe. And so they had the frequency set between 100 to 200 megahertz from early predictions and models. However, later down the line, that was incorrect. And when they ran new models, they were able to figure out that the hydrogen was so redshifted that it was actually between 50 and 100 megahertz. And so it's 78 megahertz. That was the dip in their profile that they had, which is pretty astounding. To being from 1420 megahertz down to 78 megahertz. And so from that, they can take the temperature of the hydrogen as well, and the nearby surroundings of it, from this very long equation that I could not comprehend, more or less, although I got some of the points from it. But they measured the temperature to be around 3 Kelvin, which is twice as cold as they could suspected, and there's reasons for that too. And so we'll talk about the 78 megahertz right there. So it's kind of important, very important. So using that same equation I plugged in here, we get a Z factor of 17, which is ginormous. It's one of the largest Z values to be there. And from that, they were able to take the age from it as well. And they calculated that it was only 180 million years after the Big Bang. So it's kind of cool stuff right there. And they were able to detect it with a radio telescope that was the size of a table. So it means we could do it too, maybe. Well, pitched in some money. NSF did one that. And from that, so their interpretations of the data, they were wondering why it was cold and why it was so redshifted and all of that. And so it was reported that the temperature was twice as cold because it had interactions with the hydrogen, had interactions between dark matter and baryons, which are subatomic particles consisting of 2 quarks. And if they don't know how to explain anything, they always go for dark matter. I've learned that in my readings. It's always dark matter. So from that time, they also believed that the gas and background radiation were coupled together. And they were coupled together due to constant scattering. Particles are hitting each other, sending electrons off in angles and all of that. And so, you're thinking background radiation and hydrogen were together. Well, now they're separate. What caused that? And what caused that was they also detected in that profile line was the Lyman alpha photon, which is very important. That means that there were stars around as well. They were first early stars at 180 million years after the Big Bang. And so Lyman stars, they don't produce that frequency, 1420. They produce frequencies in the ultraviolet spectrum, which is a lot more energetic than that. But it was so energetic that with also constant scattering, it kind of decoupled the background radiation and hydrogen so severely that now they're separate, more or less. And now we get the 1420 megahertz. And it's not hydrogen line. I tried to keep this a little short. We only have 2 speakers tonight, but I'm going to send you signals and yeah. I want to emphasize that no way, shape, or form am I a professional radio astronomy. So,
what did you use for a Mercier receiver?
What's that?
What did you use for a receiver to your antenna?
So I used my computer. There's new software. It's called SDR Sharp.
You have to have a detector.
Yeah. So I used an LNA. Yeah, low noise amplifier, which tunes to the 1420 megahertz, and then connected to that was a bias T which converts the analog into USB, so I can take the data from my computer. I got it from Amazon for $50. Yeah, Amazon. All that I purchased was from Amazon for $200. Besides the computer.
So the burning question for all of us, do you like grad school yet?
No, I'm taking a gap year.
That is a good choice.
Thank you. I was here for 5 years. I'll be honest.
I
People who've been to
went to
grad school would ask her.
That is a good choice. Do you know?
Yeah, it's a little,
Are
yeah, what's that?
you looking at internet programs?
Yeah, I've been a little lazy with that, I'll be honest. It's kind of nice just to relax. I know I should get on that really soon. And I know for astronomy programs, it was told to me that it's very hard to get into because they're very competitive.
If you do apply to ASU, by the way, both of us will be there. So let us know.
That would be amazing.
In fact, I'm curious who the authors were.
Bowman, Jeff Bowman?
Was Mahesh also on there?
Yes.
Okay, yeah, we went to grad school with her, so that looked actually very good. That was a little different when I was there.
I would love, Arizona is one of the top schools for radio astronomy, so if you can give me plus edges is from that.
We can just connect you with someone.
Please do, I just want to talk to them. Yeah.
Yeah, if you want to talk to maybe Mahesh, who was on there, like.
I will give you my email right now.
Okay.
because- Afterwards, yeah. Yeah.
Fantastic. My question is, you discovered a little vegetation to distance, of our radio waves. Is it essentially limitless and we just don't have the technology to go?
Oh, boy, I have a PhD. I would assume that. I think technology to also the universe had a weird moments where it was kind of. So it's kind of hard to keep compilation from season. It's really coalesce. So I did it from a relay. The telescope I have only has the aperture wide enough for our and that's I tried for Cass A. I did not pick it up there. Oh, really? Oh, yeah. Anything. The more bigger the better.
I have two questions. First, can you go back to the edges in this episode? What are
Oh, so that's the receiver box, and that was the calibration. Yeah, so sorry about that. And so they had, I believe, 3 LNAs in there, which we could have made in-house, or they could have bought inside, to be honest. I have the whole chart if you guys are interested for what I purchased. I can send that in.
Some of us, yeah.
Okay, okay. It's the telescopes here in Strong. I don't have the software here. Okay, I'll send that in email. Great. So the gamma's on the opposite side of the electron. So it's higher energy. Radio waves are longer, means frequencies are even centimeters. The gamma is no, two different, two pieces. See, I mean, astronomy, but 2 different equipments. Yeah, they're looking at different parts of the universe. Yeah, you had another question.
my second question is probably very done, but why did they detect height of that specific height? Like what stopped them from detecting from earlier?
That was there was a reason in the paper, I mean, it's not coming to mind right now, but I mean, again, it's kind of jumping around before it happened, so there wasn't a discernible frequency for that yet. The 1420 wasn't really established before that point, from what I understand.
That was at 70, so if they looked at, if they tried to detect it like 50 or like 45 megahertz, then they detect other kind of?
Quite possible, but I don't know unless I get into the case.
There's a period of reionization, so that the Vance and like there's a period of time for the potential not control. So you would have to set that to them.
If you don't have atoms, there's no way to initially force it. Early universe was too hot. First gets the initial much lower frequency.
1420. What they found 180 million. Yeah, good. Love to get my whole darn hand.
Are you aware of any way of trying to do your types of stuff together?
Oh, the infrared.
Yes. How?
No, I have no idea. I have no idea. I have a text code for radio astronomy that if I read further on eventually, it'll just know. Yeah.
Yeah. So the whole thing is you could create planet-wide telescope using.
Yeah, that's
So that first.
they did that for the black hole. Yeah, that's how they did it for the black hole. Or for the LA. Yeah, the LA is also.
It's the computer processing version that hundreds of telescopes spin all around.
Is hydrogen just like a gas that floats in space all together, just
It's
space?
the most simple element there. It's one proton, one neutron, one
Does
electron.
it just have to float around?
Yes.
That's the big questions. I'm so confused about all this. So much, Lord.
Equations that it takes.
All right.
Even scientists don't know all they did, they would have paid years.
Right.
There.
Yeah, that's right. Yeah, exactly. I just know it's right.
It's there.
Just a little bit.
Okay.
Oh, it's not there.
Thanks again, Mark. Official Lowbrow.
Right.
Miles before you run away, once you set me up for the.
Oh, yeah.
I will, mention that Miles is one of our so-called shining stars. He just graduated, we have, Avital sitting here in the back row, being quiet. She's a recent graduate too, and introduce you to Nathan Guerrero over there. Side of the room, who's our new astronomy club president coming online here for the fall. He's also a resident advisor here at the campus. Well,
I think that's even worse.
Yeah, you're fast. He helped me install this planetarium system. That's why I hate when people graduate. He also has helped me up here too.
So.
Yeah, there you
We'll try them all.
Yeah, anyway, so are we good to go here? Brian, can you hear us? And Patrick? A thumbs up? Good, okay. When the speakers were being set up here, we weren't, Patrick, you may need to kill, yeah, your audio. When we we're setting this up some time ago to perform some work for Dr. Seitzer over at U of M on the Curtis Schmidt telescope. We weren't quite sure we would have a presentation ready in time for this meeting. We have no presentation ready in time for this meeting. But you can see that, yeah, again, before I lose my train of thought on Miles, it was nice to have him here on campus, and Rosie Friend and Avital, and still looking forward to working with Nathan over here on the fun toys, as Charlie calls them. We like to give our students free hand at working these instruments and learning how to run them. And Miles learned a lot by helping install this whole planetarium system and getting it up and running. So yeah, I'm spoiled. So it is fun to be able to work with such young energy. It's good to see. So feel free to chat with them. Once we go up to the observatory tonight, you'll see how adept they are at using the instruments up there as well. So back to the Curtis Schmidt saga. Dr. Seitzer was running the telescope up till about 2017, the famous Curtis Schmidt telescope, which is now at Cerro Tololo in Chile. It resided on Peach Mountain. Some of you may know about the dome up there that's been sitting empty for several decades. This telescope was in there until 1966, and so it was used by Dr. Seitzer for satellite surveys and so forth. He can probably mention a few things about that along the way. But it sat idle for about 7 years, since 2017, when his program ended at the time, and then COVID hit, and that delayed things further. So the big question was, is it working? So Brian Ott and I were given the opportunity under the guidance of Dr. Seitzer to go down and check this out. And oh, by the way, we got to see the southern sky for the first time myself. I should have done this 30 years ago. My goodness, I've been changed by the experience. How many of you have seen the southern sky? Been down? Pretty remarkable, yes? Yes, yes. Wow, isn't it? Yeah, it's amazing what we don't see here in the Northern Hemisphere. So with that, let's move forward. Oh yeah, everything's messed up. We'll see that here in the slide. For those of you that have not been to the, getting a phone call. For those of you who have not been to the southern sky, prepare for some of the slides you're going to see, because I'm going to quiz you. Okay, it's going to be a participation. So Brian and I were lucky enough to organize the flights. Brian was very helpful in getting things organized. I took the lead on setting up the flights and so forth. We would go from Detroit to Atlanta, and then the long 9+ hour flight to Santiago, and another hour back up to La Serena, which is the host town for Cerro Tololo up in the mountains between the Pacific and the Andes Mountains. And our first night we stayed in House 9. There it is. It's a house on the campus of Universidad de La Serena. We spent one night there, enjoyed Domino's Pizza. They actually had a Domino's Pizza there. It was different kind of Domino's Pizza than what you just experienced, but it was good nonetheless. So we enjoyed the view. But the next morning we would miss the shuttle going up there. I'm sure they weren't happy about that, but miscommunication. Gosh, they speak Spanish down there, go figure. So anyways, we did manage to get a shuttle up there and went up with a couple of other postdoc folks that were working on the 4-meter scope, which you'll see here in a moment. So on the way up, we got ourselves situated at the dorm, which you see in this bottom slide here. I think you can see my cursor there, right? And those at home can see it. That is the dorm, and there's a nice dining facility there. Brian and I were set up in separate rooms. This is where the visiting astronomers stay. And if you notice, if you sleepwalk, so, yes, it's pretty high, very steep drop-offs there. And I see Dr. Seitzer smiling because he's having good memories of that too, I'm sure. But this is the view here on the right of the summit, the 4-meter and other scopes up on the summit. And there's a little lower level where a host of other instruments are kept as well. But that's the view of the summit of Cerro Tololo, which, by the way, means at the edge of the abyss. And I know what that means just by the views you're going to see. So looking from the living quarters, the dining areas, looking up at the summit, this is what you see. On the right is a Korean telescope. In the center are the mushroom farms, number of scopes, including the prompt setup from the University of North Carolina, Chapel Hill. I have a friend, a Fish Lake visitor, if you will, that will be using those scopes here in the months ahead as she works on her postdoc. And then, of course, the summit with the 4-meter dome on the left there. That dominates the view. Here is the dining hall on the left. Look at the service. I walked in there and said, this is a 5-star hotel is what this is. It's a beautiful food service, real nice dining, and just outside the windows is the abyss. So it's quite the view of the Andes Mountains from there. And you can see here Brian enjoying, yes, that's meatloaf and rice on my plate. So very Americanized meals. And they speak Spanish and English quite well. Were very, very kind to us and helped us greatly. But look at the rooms. I mean, beautiful. The bathroom, you can't see here. I got this thing in the way. Look at that. I mean, we're spoiled. This was a very nice facility to stay. And Brian and I were there for what, 7, 8 nights? Trying to remember something like that. Okay, 7 nights. So it was very, very nice. A couple of nights were very, very windy, constant 50-mile-an-hour whistling through the windows, the wind. Several cloudy nights, but that was fine. We needed a little respite anyways. This is the center of the round operations room up on the mountaintop. And you check in here and check out here. And you can tell that it's winter. Look at the tree. Here it is in June. There's no leaves on the trees. So their winter obviously is our summer and vice versa. So Brian and I were subjected to some pretty cold temperatures up on the mountain. Good thing we brought the long underwear. But we were privy to a car that got us from the dorm up to the summit. In the background, you see the U of M Curtis Telescope Dome. There are several others here on the summit, which you see here in our views. And to our right is the 4-meter dome, which is looking a little shabby in these views, but there's insulation stuff that they're going to probably undoubtedly put on, but I'm sure it's not cheap to maintain these instruments. We were amazed that there were some plants able to hold on to life up there at the summit and in the gravel. And again, here we are parking in this parking area. So we drive up and notice the clouds, plenty of clouds. So note that. On the left is the ops room of the Curtis Schmidt, the Cerro Tololo computing staff. The IT folks were very, very helpful in establishing, making sure we had internet first off when we got in there the first day. The gentleman right here next to Brian is Javier Rojas, who's more or less our go-to guy in the operation of the instruments and getting things up and running, and helping Patrick back home, who was conferring with Brian, getting the Zoom link established so that Professor Seitzer could guide us on what we needed to do while we were there. On the right, we're at one of the many beautiful meals, lunch and dinner. We even had breakfast, but who goes to that? I know Brian did a few times. And on the lower right are the postdocs that I mentioned that we had with us while we were there that week. They were working on setting up a camera for the 4-meter telescope that they would use at Kitt Peak. So they tested it on the Blanco, which is a parallel instrument to what's on Kitt Peak. There is the Schmidt. This is a picture taken by Brian. I'll let you read the data. This comes right from the Cerro Tololo webpage. This is Dr. Seitzer's project here. Patrick, did you want to say anything about this? Oh, you got to click your audio on, your microphone on.
The only thing I would say is that we did submit a modest proposal to NASA for funding. I hope you can hear me. And
Yeah.
It was successfully funded. And we do not eat our young in the orbital debris community, with apologies to Jonathan Swift. So anyway, I'll let you continue. So I would say how this visit came to pass is that both Brian and Norbert approached me last year and said, well, we're going to Chile to do some astrophotography. And we're planning to go up to the north. And we just want your advice on things to go. And I thought about this for about 30 seconds. And I said, I wonder if I could convince them to go by Cerro Tololo and check out the Curtis Schmidt to see what its status is, since it's been 7 years since it was last used. And I could think of no people better qualified to do this, given Norbert's experience with toys, telescopes of all apertures on all sites, and Brian's experience with remote observing and everything, and computers. And the deal was they paid for their airfare, and the Michigan Astronomy Department would pay for all their expenses up on Cerro Tololo, transport, food, lodging, and everything. And I'm happy to say that it worked out spectacularly well, much better than I had hoped. The telescope is in much better shape. And with that, I'll turn it back to you. And with what we do with the telescope, well, it's entirely supported by external grant support, for which we don't have any at the present time. So we'll work on that for the future. So let me figure out how I can mute myself and unmute you at the same time so I don't interfere.
We're experimenting with our new OWL device here, so it's been a little glitchy, but I think we're managing to communicate to those folks out there. But as you can see, this is the scope in its so-called service position on its back. For me personally, it seems awkward to see the scope, but this makes it very reachable. We could get to all the components, including the large black device, which is the very expensive and quite capable CCD imager that Dr. Seitzer used for his cervix hanging off. It looks like, yeah, that's right. Yeah. But here's another interesting thing. It's a good point, Charlie. The polar axis is aligned to the south celestial pole. And for a veteran of northern hemisphere observatories, looking east relative to the axis, I couldn't wrap my head around that. It was very daunting to retrain yourself after 40 years of 50 years, a long time of using scopes in the northern hemisphere. This gets pretty awkward. So anyways, there you go. And here's Brian giving you a sense of scale of the instrument with it in the zenith, or the vertical mode, which is another one of the positions it parked in. For many years in lectures here at the university, I would show this picture of the Curtis Schmidt, and this gentleman here, Dr. John Graham, a very young Dr. John Graham in 1968, seated at the eyepiece of the 8-inch guide refractor on the side of the instrument. And I couldn't resist doing this, sitting in that same chair, which happens to be in the observatory in 2024. He was sitting in it in 1968 and sort of struck a similar pose because I couldn't believe that I was actually sitting there after all these years. So I had to take a picture of that steel case chair, which is still there in the dome. I thought that was fun. What a privilege to be there in the shadow of this instrument. So a lot of fun it was had by Brian and I, Dr. Seitzer. So pretty cool. So there it is. It's a beautiful instrument. Strangely enough, it's one of the smaller telescopes up on the mountain, but does what it's designed to do, and has some interesting qualities to it. We got to look visually through the refractor at some select objects, but our window of opportunity to do so was limited to just 1 or 2 nights because the wind was just too much for us to open the dome safely on the other clear nights. And we had plenty of cloudy nights too. Gosh, their June is our December. You know how cloudy it is here in December. So that was the situation. But again, here's the telescope in its service mode, pointing east, which makes parts of the instrument accessible, including this hatch door. I opened that. Brian and I were peering at the main mirror and the corrector plate and the camera across the way. So pretty neat. This is called an English equatorial mount, the counterweight offsetting the tube. There's the CCD camera on the left, some of the ganglia hanging off on the right, and all very functional and specific to the use of the instrument. It also has some intriguing spectral filters that go in front of the corrector plate. Each of those is about 250 pounds. Not exactly light, but in their day, they were quite useful for the spreading of light across the spectrum. Pretty cool. Here is the ops area. The system uses a DFM controller, which is basically the same as the one in Angel Hall up on the DFM 16 and the one at U of M Dearborn. This is configured specifically for the Curtis Schmidt telescope. So it has its idiosyncrasies as well. And it's all in the gentleman's head that's sitting behind me here, Dr. Seitzer. He knows this telescope like the back of his hand, and it was fascinating listening to him control it all the way from home here in Ann Arbor with the scope down there in Chile, using the software and getting things hooked up. And thankfully, Brian's expertise at doing all that hookup stuff was fun. I just sat there and enjoyed the views. And I oiled things. That's my forte, is oiling joints, which is part of what we did. But here's the control panel. By and large, most everything worked except the device you see on the left, which is a GPS clock. It sort of outmoded itself. A new one is available, mayhaps will be purchased to bring everything up to speed. The time sync is important with the operation of the telescope, but there's the pointing software and the control software of this system. It works. It's pretty neat. So some pretty pictures. Here is the view from the summit, again from the parking lot. I'm going to move our guys over here so I can see this. In the distance, if you can see my cursor, is Cerro. And Cerro is home of the Gemini South telescope, the SOAR telescope, and this thing called the Vera Rubin LSST. You may have heard of that one. That's coming on next year. There were crews in the dining hall eating and enjoying chit-chatting in Spanish that would get on a bus and head on over to do work up there on the mountain as they continue to construct and finish up that instrument to come online next year. So pretty neat to be there in this environment. And look at this lone tree up on the summit there. It's pretty cool to see that at night. You'll see that in some of our pictures here. So again, not too far from the Curtis Schmidt, which occupies very prime real estate there at the summit. We find the 4-meter Victor Blanco, which is 4 stories up. We had to take an elevator to the 4th floor to get to the telescope itself. There's also 1.5 meter, so-called smart telescope, and a couple other instruments you'll see here shortly with that. Those other instruments are in these domes. By golly, they all start looking the same. They're all white domes, go figure. You can get crisscrossed easily. But here again is the Curtis Schmidt. And the smaller one way over here, surprisingly, is the U.S. Naval Deep South Observatory with a relatively new plane wave 1-meter scope in it. So pretty nice instrument set up down there at the summit. And just over the edge, the abyss. It's pretty amazing. I had to pinch myself to note that I was actually here. And in fact, my upper echelon would be remiss if I didn't use the banner and send this back home that I was actually there at the summit. So pretty nice. And again, thank you, Dr. Seitzer, for the opportunity. I appreciate that. Here's a few other weather views. And we found ourselves amongst the clouds on occasion. If you had a wig, it would get blown off. It's very windy up there on occasion, and we did find ourselves inside misty clouds. I estimate this valley over the edge probably a good 3,000 feet down, because Vicuña, the little town beyond, which you'll see in the pictures, is 5,000 feet down, full mile down. And Cerro is 9,000, almost 9,000 feet. We were at 7,200 feet here at the summit of Cerro Tololo. So you can see the clouds, the snow in the mountains. There were some really gloomy days, but I didn't care. We were there. It was pretty cool. And again, appreciate it. But this is the view from the summit, looking towards the Atacama to the north. And every day we were there, Brian and I would come out and look, and it'd be clear over at Atacama, which is the driest place on earth practically. It's always clear there, clouds where we were at. So I found that quite interesting in that observation. But look at the vista that you have from up there at the summit. Absolutely amazing down there. Our service road, it's an hour trip from La Serena, came up that drive. Somewhere down there, there's a gate, a guardhouse. They're very tight on security there. They don't let any old person come up there. But again, these are the views of the Andes from the summit. Pretty neat views. We're approaching evening here. You can see from the summit, I was standing right by the Naval Observatory telescope when I looked down and saw the dorm here. The ops room is over to the right. This is the mushroom farm. These open clamshell domes are the prompt telescopes at the University of North Carolina, Chapel Hill. One young lady I know, Megan Dubé, will be going down to Cerro to work on the UNC telescopes. She's working on her postdoc. There's Vicuña in the distance. That's at 2,000 feet above sea level. I'm standing at 7,900 feet when I took this photo. And these Andes mountain ranges are averaging about 16 to 17,000 feet in the distance. That's the border to Argentina over there. So, quite the magical view. And so here we are on the one beautiful, precious night. Brian and I getting ready to observe. They have the doors open on the 4-meter, getting it cooled down, getting it ready for observations that night. We couldn't believe they opened that dome even in 50-mile-an-hour winds. It was pretty stunning. You could hear it howling up there in those rooms. But here we go. Here's quiz time. Again, keep in mind you're 30 degrees south latitude, 71 degrees west longitude. Pick your favorite constellation over the Curtis Schmidt dome. I see heads being twisted sideways. Keep in mind the Milky Way's nucleus passes directly overhead. We miss half of the galaxy here in the northern hemisphere. Those of you who have been down south, you know what I'm talking about. You can see the galactic bulge. You can figure out things there that you just can't figure out here. I'll give you a few clues. There's Antares. Okay, there's the 3 lead stars of Scorpius. Yeah, there's M4 right there. And by the way, these pictures are not much of an exaggeration to what we saw. I mean, it's pretty remarkable to see the Milky Way like you see it down there. Here's the tail of Scorpius swinging around here. There's the stingers, Lesus and Shaula. Stinger Scorpion. This is M7, the Ptolemy cluster. And this is a Sagittarius star cloud, the spouted Sagittarius behind the dome coming up in the east. So the Milky Way rises in the east, and it's opposite to what you are accustomed to seeing things rise here. Keep in mind, when you're looking out in the east here in the northern hemisphere, you see things leave the horizon sort of on a right trajectory, a right path. In the southern hemisphere, it's on a left trajectory. You look north to see the constellations moving across the sky, much the same way we look south to see the constellations moving across the sky. So everything's backwards. I'm going to really quiz you on a good one here in a moment. But again, here's Antares. Look at the nucleus of the galaxy. This was incredible. And I truly believe that if philosophers and astronomers of Renaissance Europe had seen this, it would have changed their view on things. It really would, because it is a marvelous thing to see in person. Truly is. Another one of my scrub shots here of the Milky Way. I was using an 18mm lens. Here again is Antares for reference, right there, and the Stinger Scorpion. The Ptolemy cluster stood right out, couldn't miss it. But off to the right here is our nearest star, Alpha Centauri and Beta Centauri there. This shining little object, this jaw dropper is Omega Centauri. And so Brian and I were very lucky and impressed to see it through the refractor on the side of the Schmidt. It's amazing that we're there in the realm of all these big telescopes and couldn't look through any of them. But it was quite remarkable. It's a 75-year-old instrument, but has a little blue scatter there on it, but it conveys the idea very nicely. This M13 is small potatoes compared to Omega. And another globular I'm going to show you here in a moment is pretty incredible too. So here is the Milky Way over the 1.5-meter dome. On the left, what are those? Yeah, there you go. That's how they looked. There wasn't, think I see them. No, they were sticking out like sore thumb. Could not miss the large and small Magellanic Clouds. And this apparent star-like object right here above the small, that's 47 Tucanae, the globular cluster. And another spectacular globular that puts M13 to shame. So I am terribly jealous of the southern skies. They have so many stars. I couldn't believe how many first and second magnitude stars I was able to just gather in and look up. And Brian and I were sifting through the sky with binoculars, and I saw more open clusters than I could possibly count. I wish I had my 18-inch Dobsonian sitting there, but no, it's 5,000 miles away at Fish Lake. It would have been glorious to see all this stuff in person. So again, here's a nice view of the Magellanic Clouds. Again, more or less what you see when you look up there at the night sky. And by the way, over the 4-meter dome, you see a hint of the Southern Cross, and the coal sack stood right out. Could not miss the coal sack in those skies. Pretty incredible to see visually. Here's a better view of the Milky Way passing over the 4-meter dome. So look how obvious the coal sack is there relative to the Southern Cross. Over here to the right is the False Cross. You may have heard of the False Cross. This Avior, this star here, is a distinct red, Betelgeuse-like. And here again are Beta and Alpha Centauri. We did look at Alpha Centauri through the 8-inch refractor on the Curtis Schmidt and easily split into a beautiful, slightly offset yellow pair. Wonderful to see. Why can't we see that up here? I'm so sad. But look at the number of stars. This is just incredible to be in that sky. So again, here's the nucleus of the galaxy, which passes directly overhead. You could easily see from Cygnus to Canopus, the stretch of the Milky Way overhead. So beautiful. Here's where I want you to really stare at this one. This is looking north over the Schmidt dome here on the right. Recognize any constellations? Keep in mind we're looking north. I don't see anybody standing on their heads yet. I'll give you a hint. There's Arcturus, about 20 degrees off the northern horizon. Lyra Vega was about 10 degrees. No Big Dipper. We saw maybe 1 or 2 stars of the Big Dipper's handle come up, but that was it. You don't see Cassiopeia, you don't see the Big Dipper. I'll give you a clue. Over here is the Sickle. That's Leo, upside down. Here's the tail, there's the nebula. This is Coma Berenices, upside down. So again, everything's upside down. You see Boötes upside down. You see Cygnus upside right. The neb's down, the head's up, so it's flying upward. So everything's upside down backwards. And again, once you get inside a telescope dome, that really plays with your head. You can't teach an old dog new tricks. I was struggling, okay, but it is beautiful to see. And a couple more magical shots. Here's Corona Borealis, so we would have been able to see the nova, which didn't happen. We're still patiently waiting. There's Coma Berenices up there, and these are 2 interesting shots. What phase of the moon are we looking at here over La Serena? Almost new. That could be either side. An old moon. So your instinct says, hey, that looks like a dawn moon, doesn't it? Waning crescent. That's a waxing crescent moon near Pollux and Castor in Gemini. Okay, so it's backwards. It's upside down. South is up again with the moon setting in the west in the early evening. So it is definitely messing with your brain if you're accustomed to seeing things.
Sorry,
This is,
I have to interrupt here, but
go ahead.
things are not upside down. Okay, they're
Okay.
upside down in this hemisphere, in the
Yes.
northern hemisphere.
That's right.
They're
yeah,
right side up in
yeah.
the south. Okay,
Thank you.
back to the show.
No, I appreciate that. Yeah, I'm insulting every Australian and South American that ever lived. But yeah, I agree. But again, Patrick, I'm spoiled by the Northern Hemisphere. And frankly, when I come back to the Northern Hemisphere, I'm sort of bored by it. In a way, I didn't say that, but yeah, it's definitely weird. This is the view stepping out of the dorm to see the coal sack and the Southern Cross, and Alpha and Beta Centauri was quite magical. Now, Brian, here you are. this is your time to shine with the panoramas. Here's some of the views that Brian took, and I'll let you explain them if you can.
Well, I just got to say that first bucket list item, the total solar eclipse. Then 1 month later, another bucket item, the spectacular aurora display. And then 1 month later, going down to see the southern stars for the first time. Well, I said to my wife, I can die now after those three things. So yeah, it was spectacular. And as Norbert said, we had a wonderful, spectacular one night that was amazing. We had another night that was also very good, but it was windy. But yeah, we had an amazing night. And so I just took a vertical shot, 4 of them across, and then put them together in a panorama. And it was, when we were there was so much air glow. There was a lot of air, as you can see here. Not all these are clouds, especially to the right. That's red air glow. We have green air glow and red air glow. It's just so. But the dark clouds in the Milky Way suddenly just pop out, and it was just amazing to see. So it was just a magical night. And this is the core, and it was the first time ever in my life I realized, wait a minute, yeah, the Milky Way has a core, it has a bulge at the center, and this is the bulge. And you can see the lines moving towards, the Antares and Rho Ophiuchus, and then there's the Zeta Ophiuchus, and Norbert's, that's lagoon. Yeah, I mean, you can see the lagoon, the Trifid, the eagle, the swan, all of them moving up and down, and some stuff on the upper right, I didn't know what they were, right? And the nice, what's that?
Nebula.
Is that the Eta Carina? Yeah.
Eta Carina, yeah. And you were impressed with the southern crown.
The southern crown was so pretty. Yeah, look at that, very cool. And then you can see and to the left of that, you can see the Sagittarius, and and so the center of the galaxy is very close to the center of this picture. And in fact, I put a black dot in the middle, real small. And maybe this is over processed, but we've got the Milky Way kind of going straight across. This is my extreme processing version, but you can just see, look at the air glow. I mean, it was just, and you can see it in waves. It was spectacular. Yeah, it was, and you can see the small Magellanic Cloud, little peeking out there. Yeah.
47 Tucanae again. Brian, did you want to tell them how you cheated here?
Well, you can see that I painted the observatory. It needed a good painting, and it was detracting from the pictures. And I will tell you, the new generative fill AI in Photoshop is magic. You just select it and you give it the words fill within the lines, and it fills within the lines. There's the same thing, but less extreme processing, but just an amazing time. And I think there's a city in the lower right. That's the glow, and the green to the lower right. That's down the coast towards Santiago, but probably not Santiago because it's pretty far away.
All right, I'm going to come back to you for the time lapses here. I've just got a few little panorama views to show, and then we'll wrap up the presentation here with this. This is a typical sunset. We saw some gorgeous sunsets there on the mountains, and the valleys filled in with clouds. Quite beautiful. This is stepping off to the edge of the dome, the view you would get looking towards the Andes and down into the valley below. So quite beautiful vistas. I took the picture on the right for some of my geology friends. You see a lot of this pillow rock up there. And a few of the other scopes on the mountain, the 1.5, 1.2 meter scopes as well, in adjoining domes and some of the ops areas. We were privileged enough to get a tour of thanks to the postdocs, of the 4 meter Victor M. Blanco telescope. Here's the entry lobby. This intriguing telescope sitting inside the lobby. But here are the control screens that you see on the first floor level, the telescope level. But here's Brian standing at the base of the 4 meter telescope. which was being calibrated when we were up there, so they had the mirror covered. But you can see the white flats up on the dome and so forth, and some of the camera work up at the prime focus of the instrument. So it is a 1973 vintage instrument, akin to the Mail reflector on Kitt Peak, sort of a sister telescope, similar institution, built about the same time. And this was the drive down from the summit. You come around this bend, and that was your view heading down to the dorms, which are just below this summit here. And there's the Naval Observatory telescope. I was amazed at this little telescope that's fixed out there all the time in the weather and everything that you can sit there. It's actually aimed at Cerro, so we could look across and see the Vera Rubin telescope being worked on with that instrument. And from the the South Korean telescope, this is the view of the dorm and the ops area and Cerro. You can actually see the Vera Rubin dome there and the Gemini South dome right there. So pretty nice vistas. And this is from the back of the Korean telescope, the view towards La Serena. So everywhere you looked, the views were absolutely stunning. So we were very happy to be there. There's La Serena. We had to land in that fog. It's always fogged in there, it seems, but quite the views from up there. And they got a cute little airport at La Serena and La Florida airport, and their computer system went dead. So they did things the old-fashioned way, by hand. One of the ticket agents was using your cell phone to call the other airport to get us logged into Santiago. But there's the views. Let me come out of this real quick. Let's see, I'm gonna stop the share here for the moment.
Yeah, in order to get my boarding pass, I had to hand her my phone, and then she Gmailed me our boarding passes from her personal phone.
Yeah, they just got the crowds right a couple months ago.
Brian, I'm gonna set this up. I think I can share.
Yeah, I just set up the camera just pointed up to the sky and took images every 30 seconds and put them together in little short video clips. So they compress time by 60 times, and these are just short time-lapse videos of various things. This is the big scope moving and the Milky Way dropping behind it. Eta Carina is that bright red one falling down, and the other red lights are cars driving down the mountain.
There's Eta Carina there, and the
Yep.
coal sack.
The coal sack right there.
And
Yeah,
this
it's
is
just
lane through Centaurus. We don't again see that.
the death lane is shocking. And oh yeah, and the lower left is the is that the small Magellanic Cloud?
Yeah, that's the one creeping up from behind. No, actually, that's the large one. The small
That's
one's
the large one there?
Yeah.
Yeah, that's the
You'll,
big
you'll
one.
notice a lot of airplanes off to the left. There's a major north-south route to Santiago along the Andes Mountains. So this is one example of a time lapse. Let's see if we can get another one here. There we go. This is Brian's Milky Way over the
Curtis Schmidt. Yep, and lots of clouds, but it's kind of interesting. Lots of airplanes as well.
I'll let this loop for a few times here.
Yeah, it's just coming up,
Again,
and you know,
there's Alpha Centauri and here's Antares.
and you can see the horse, the dark horse in the Milky Way. You know, that's close to Scorpius. That was obvious. I've never seen it so obvious in my life, because it's straight overhead at late at night.
Okay, here comes another one.
This
Here's
is
your
the
Magellanic Cloud.
The dance of the Magellanic Clouds. Yeah, they're going around the South Pole. And interestingly, you can see the waves of the air glow there. You see the green and the red waves moving. That's air glow.
47 Tucanae, the globular. Nice views.
Yeah,
So-
the Magellanic Clouds, very cool. And that's the core coming up. A lot, just tons of red air glow in that direction. Just tons as we look to the east. It's just very red, and then also a lot of airplanes.
I'm amazed by this cloud on the lower left, which seems pretty stationary over the Andes there. But yeah, these views are absolutely spectacular. I think we got one
So
more.
I would say that most of the objects you see streaking are satellites and
Okay.
probably not airplanes. Because you would see the flashing lights on the aircraft and you wouldn't see them on the satellite.
Okay.
This was one of the last nights we had, and it was just a beautiful night. And then you can see the clouds move in, and they
Actually,
move in and out.
produces a nice effect on the color of the stars. You can see Alpha and Beta Centauri, a very distinctly blue and gold difference, and the Coalsack.
Yeah, this is the lazy way to do astrophotography. You just set up the camera and just let it go and go inside and warm up.
We did not want to go to bed because it was just too beautiful a sky to leave.
Although it never froze. Okay, we had some nights where it got down into the low 30s. We never had a hard freeze.
Okay, with that, I'm going to show these folks here in the planetarium a short little video called Big Astronomy, which deals with astronomy in Chile. I think you will love it here in this dome. The others online are welcome to stick around for a minute. Any questions from anyone online or here? Yes.
So the highest got up about 7,800 feet. Do you ever have any breathing issues?
Nope.
And, okay, and two, the Prof Schmidt can set up digital imaging. It appears as though you put there's flat and then some sort of a shield flattener to make it work for a flat.
On what now?
On the Schmidt.
On the Schmidt, it has a proprietary lens that's designed by the company, according to Dr. Seitzer, that was designed for that camera. So they didn't just stick a CCD
Because
camera.
normally you have a
Right,
photographic plate,
right.
a curved photographic plate.
No, there must be
a flat.
there's a proprietary lens in front of the CCD for that purpose. Yep. And it was expensive. Yeah.
The time lapse of photos, right? Obviously,
No, just your standard air glow akin to what you see in your auroral colors.
Very low, and the film, since, let's see, light of the combining. Yeah, like, maybe it's the upper atmosphere.
Okay. There you go. Thank you. Actually, there was a professor there who was actually taking all sky images of the at the summit the night Brian and I were up there, taking some images ourselves. So we were being very, very cautious, but people were coming and going in cars up to the 4-meter scope during our survey. So we weren't sure how Dr. Connie Walker was up there. She was up there doing a survey of the all sky. Anyone else? If not, again, I'm going to pause this and let take the screen sharing offline here. Brian and Dr. Seitzer, are you all set?
So I think I'll drop out here at the moment and just say what a pleasure it was to have the two of you be able to do this expedition for us. It was extremely helpful. We're glad there was enough clear nights that it was worthwhile for you to do the astrophotography. And again, thanks very, very much for this expedition. It worked out very well from all concerned. So, and I would just say about the curved focal plane on the Schmidt, it is the Dewar window was replaced with a single element quartz lens to act as a field corrector, as a field flattener. it's only, we have 1.5 arc-second pixels, and we were only interested in 4,000 to 8,000 angstroms. So it wasn't a particularly challenging optical element to fabricate. The question was just to make sure it now seals the vacuum instead of the door window. So with that, thanks again to both of you, and to clear skies everywhere.
Thank you.
Brian, you're all set? Thank you, sir. Okay, I'm gonna let that run. Miles, you wanna pull up, pull this overhead? We're just gonna share with you the beginning of this beautiful program that we like to show here at the planetarium called Big Astronomy. It deals with there we go. Uh-oh. Oh, no, we got that out. Let me pull this up. You keep that. I'm going to do a. One moment, please. Cool. Now, this is a neat little video called Astronomy. Turn up the volume.
Filled not with distant, lonely stars, but with countless families of planets. I want to share some of these family stories with you, where they come from, how they take shape. But I also want to introduce you to where I come from. A place where astronomers study the sky, with the help of amazing technology and even more amazing people. A place where people have experienced a strong connection to the night sky for millennia. I want to introduce you to astronomy in Chile. Chile lies on the west coast of South America, a long, narrow, mountainous country. The Pacific Ocean lies to the west, the towering Andes Mountains to the east, and the Amazon rainforest to the north. Chile is perhaps the best place in the world for observational astronomy because of its special climate. The Andes block rain clouds from the east, while currents in the Pacific Ocean bring cold waters north from the Antarctic. Along the Chilean coast, the air temperature drops, and as the cool air sinks, it loses its moisture. These factors combine to create stable dry air over Chile's coastal mountains with few clouds, perfect conditions for astronomy. Many major telescopes dot Chile's mountainous terrain. We will visit just 3. These observatories are looking at places in our solar system and beyond to help astronomers understand where planets like ours come from. Standing on the side of this mountain, you can understand why it was named Cerro Tololo, which in the Aymara language means at the edge of the abyss. Cerro Tololo Inter-American Observatory is home to dozens of telescopes. Let's take a look at the largest, the Victor M. Blanco telescope, with a primary mirror 4 meters in diameter. Astronomers designed this telescope to observe the same kind of light our eyes can see. It's an optical telescope. Light enters the large opening and bounces off the giant mirror. It's the first thing the light hits, so we call it the primary mirror. The bigger the mirror, the more light it can collect. So astronomers like to build large telescopes to gather as much light as possible. The shape of the mirror focuses light on a giant lens, more than a meter across. That lens is part of an amazing instrument called the Dark Energy Camera.
Dark energy camera has 62 science detectors, one of the biggest cameras in usage in the world right now.
Marco Bonatti is the first of several people we'll meet who keep these observatories running. As an electronics detector engineer, he's responsible for what happens inside the instrument.
And to be very careful that they are clean all the time, because otherwise you have all sorts of stuff deposited in the surface, and the surface is especially coated. Basically, we want to avoid any dust particles. So in the clean room, we have a controlled environment. We can control the amount of dust inside by basically having filters and positive pressure that keep the dust out. All the light that the telescope gathers goes to a single point, basically. At this point, into the detector. So the detector you put there depends on the science you want to do, on the instrument, and a lot of factors.
Once the instrument is out of the clean room and mounted on the telescope, other team members help make the observations.
My name is Jacqueline Cerro, and I work at Tololo Inter-American Observatory. My position is night assistant. This means taking care of the instrument and having the telescope ready, taking calibrations, and making sure that everything is working fine. And during the night, operating the telescope, which means moving the telescope to the position that the observer wants, and making sure that everything is working correctly. What I really like is to learn in general how the telescope works, how it takes data, and all these different systems that are interconnected and that accomplish such a huge task, and all the engineering involved. It's amazing.
Let's hear more from Capi Vivas, a Venezuelan astronomer living in Chile.
I am part of the support team of one instrument in the Blanco telescope, the Dark Energy Camera, which is a wonderful instrument. It's special to make surveys to cover large portion of the sky. As part of the support team, we make sure that the camera is producing science quality data that is ready for astronomers from all around the world to come and do their science projects with the telescope, and that they can achieve their science goals with this instrument.
The dark energy camera was designed to peer into the farthest reaches of the universe. But because it can observe a large portion of the sky, it also helps us search for objects much closer to home. Leaving Earth behind, we see the orbits of planets around the Sun. Mercury, Venus, Earth, and Mars. Jupiter, Saturn, Uranus, and Neptune. But our solar system includes many other objects, not just planets. Astronomers have used the dark energy camera to find numerous small icy bodies in the outer reaches of the solar system. We have tracked thousands of these objects, which reside far away from the Sun, past the most distant planet, Neptune. They make up what's called the Kuiper belt. Billions of years ago, everything we see here likely revolved in the same plane. But the massive planet's gravity tucked the lightweight Kuiper belt objects into different orbits. They now travel of the planet's orbits. Each tiny icy world we discover helps us answer questions about the history of our solar system. What did it look like billions of years ago when the planets were taking shape? We can't go back in time, but we can observe other planetary systems in the process of forming. This work requires our most powerful telescopes, so let's return to Chile. We're heading to a mountain called Cerro only about 20 kilometers from Cerro Tololo. Here we find the Gemini South Observatory, which began viewing the sky in 2002. Inside the dome, we can see the giant telescope with a mirror more than 8 meters across, more than twice the diameter of the Blanco telescope. This giant mirror must remain highly reflective, which means it needs cleaning every week. Such a big job requires a lot of teamwork.
My name is Vanessa Montes. I'm an electronics engineer. We have different disciplines like optics, mechanics, electrical, software also. We all work very well. It's a lot of team effort and a lot of collaboration between everyone. And I think that that's very positive. The more you can encourage people to participate more creatively in the different projects that we do, it's a more collaborative work environment.
Cooperation on Gemini extends around the globe. Astronomers rarely travel to Chile to use the telescope. Instead, they telecommute. Here, in the Gemini base facility in the coastal town of La Serena, nearly 100 kilometers from Cerro Batón, technicians can operate a special instrument that looks at young planetary systems, called the Gemini Planet Imager, or GPI. Almost 10,000 kilometers away, at Stanford University in California, observers see the same displays and guide the work with GPI. Astronomers need somebody they can trust on the other end of the line, and that's where Alicia Shugart, Science operations specialist comes in.
We operate the telescope at night. We take data for the astronomers who have all contributed proposals for science. I really enjoy observing. I think about it as if these photons that literally are billions of years old are arriving and I'm seeing them for the first time.
Not all photons are billions of years old. Many were created more recently, closer to home. Light detected by GPI reveals what happens when planets form around nearby stars. We can imagine traveling to one such place, so far away that its light takes more than 60 years to reach us. This star is more massive and much brighter than the Sun. The star and its planetary system are less than 30 million years old, mere infants compared to our own middle-aged solar system. Dust and debris form a disk around the star. Some tiny objects in this disk will end up like our Kuiper belt, icy bodies at the edge of the system. GPI allows us to peer into the center of the disk. Astronomers then use computers and the laws of physics to simulate what might be happening. We have discovered one giant planet, more than a dozen times more massive than Jupiter, whose gravity has sculpted the dusty disk into a warped spiral. Could something similar have happened in our solar system billions of years ago? For the next part of the story, we must now travel much farther north in Chile, to the Atacama Desert, one of the driest places on Earth. Home to a collection of 66 radio antennas, the Atacama Large Millimeter Submillimeter Array, or ALMA. The skies of the Atacama Desert are famously clear, and people have observed the sky from here for millennia. David Barrera is president of the indigenous community of San Pedro de Atacama.
I feel that the cosmos walks with me. It walks with you, with humanity. It is part of our life. We humans are nothing compared to what the great cosmos is. That is why we are part of the cosmos. We walk together. We make up a single unit. That is the marvel of the human understanding. Alma has been a respectful neighbor because it has asked what is the ancient wisdom of the native people in regard to the cosmos. And Alma's invitation to the indigenous community is in some way to unite scientific knowledge with indigenous knowledge.
Astronomers have come to this unique spot on Earth to build an array of telescope antennas that benefit from the clear, dry skies 5,000 meters above sea level. These giant antennas work together like a single enormous sky in unprecedented detail. And they can work both night and day. Each dish weighs about 100 tons. And they need to move from place to place, both to make different kinds of observations and to receive maintenance when needed. Alfredo Algueta is one of only 4 people trusted to operate the transporters that move the telescopes.
The transporter has just one basic work that is designed to do, and it's move this big radio telescope from one point to another. When you're doing the maneuver of trying to load the antenna or unload the antenna, you have to do it with the remote. But when you're doing the translation from one point to another, you have to do it from the cabin. So every time that an antenna needs like a big fixing or anything, we try to bring it down, but it takes a lot of coordination to do that. It takes around 5 hours, driving 5 kilometers per hour.
Once antennas are in their correct locations, they collect a huge amount of data, and they work as a network. Data from each antenna is compared to data from every other one. Celia Verdugo, an astronomer and data analyst, collects and studies these observations for astronomers from Chile and other parts of the world.
The kind of light we are collecting from the sky is a light that is emitted in radio wave shape, see? We are looking at the parts of the universe with the lowest temperature, and because of that low temperature, they emit their energy through radio waves. We collect that signal, and from that, we can get either spectral information, or we can also get images of the source we are observing. And we're taking data for projects that are breaking the limits of what we know, going beyond the limit of our knowledge. That is really fascinating, yeah.
One of the ways ALMA has revolutionized our view of the universe is by giving us a close-up look at young planetary systems. Here, we're seeing not just the leftovers of planet formation, but the actual disk of material from which planets take shape. This is ALMA's image of BDS 70, a very young star, less than 10 million years old. Its debris disk looks more like a ring of dust surrounding the star, with a large gap where at least one Jupiter-sized planet is forming. That planet has a small disk of its own, where moons could be forming around it. Here, we're seeing the results of a computer simulation, which we can compare with data from ALMA and other telescopes to help astronomers understand how planets grow. Perhaps our solar system looked like this billions of years ago, a family of planets taking shape. Pioneering work in astronomy requires investing in the next generation of telescopes. When completed, this telescope will observe the entire visible sky every few nights. It will generate 20 terabytes of data each night, twice as much as the Hubble Space Telescope generates in a whole year. All the data will be made freely available to the world, enabling anybody to make the next great discovery.
That was the Bureau of School.
The future of astronomy lies in all our hands. That's why I enjoy meeting with students of all ages. I hope some of them will grow up to work with me at one of Chile's great observatories or elsewhere in the world. All of us you met today come from different backgrounds with many different talents and skills to contribute. We invite everybody to look, to learn, and to enjoy astronomy. We hope to share the wonder of the sky and the excitement of discovery with the whole world.
You enjoyed that? Making of this film, Dan Tell was a longtime Grand Rapids native and Planetarium associate now in California, and Dr. Shannon Schmidt, the director of the Abrams Planetarium, is in the credits as well. So go to that website, you learn about all the stuff of children. Very cool stuff. With that, I'll turn it back over to Charlie, and then we'll invite you to wander up to Sherzer. This is actually.
One more question.
Yes, sir.
You were imaging the sky.
Yeah.
You could actually see the waves.
Well, we could see the band patterns and stuff, yeah. The stars, what you saw in the night sky, the Milky Way, was not dissimilar in the photos to what we saw with our eyes. The dark lanes in the Milky Way just stood out like a sore thumb, especially the coal sack. Yeah. Well, half the people in this room raised their hands, so they know what I'm talking about. Right? If you were in a dark sky site like we were in Cerro Tololo, it was absolutely incredible. I seriously came back to Milky Way and went, oh.
Yeah, you're ruined. Forever.
Yeah, I am ruined. I am ruined. Yeah, so definitely is weird.
You feel bad.
Yeah. I'm sure Brian can share many of the same thoughts. So anyways, thanks again for watching that. And Charlie, I'll turn it back to you. Yeah.
I think mine was kind of not full switch.
Yeah.
A little bit better. Yeah. And then I'll more buttons.
For officer reports, I just wanted to remind everybody that next month we're having no guest speaker or anything. It's going to be alcohol, Kathy, and Kurt Bennett. We actually did one 15, 20 years ago or so. It's a long time ago. It was a lot of fun. So you already saw something come out by email. We sent out another one. That's a link to a list online. You can put in there what people are bringing, what you want. So.
Just want to point out, we will not invite moving on Zoom.
Yeah. It's kind of hard to get them through that. And I'll leave this to Jack. I was going to mention Michigan Math and Science Scholars. Next week, I'll leave that to Jack. In fact, where's Jack? I'll turn it over to him right now. Go ahead.
Okay, just make it real quick. We did have the last Michigan Math and Science Scholars program on the 11th. That was the rain day. And so for the tournament night there, they held it up. Anyway, the next one I think was on the 29th. Observatory there for that. And still working on getting the door lock. Other than that, should be good for the rest of the open houses. Sky conditions, we plan on coming out to the observatory.
Ken?
Well, I have to report, so that makes sense.
That's correct. Thank you for taking the minutes. Brian, I think he's still on Zoom.
No, we lost him along the way.
Okay.
He's seen that Cerro Tololo stuff. He's
Yeah. Yeah. Amy.
Yep, no.
Wow. All through that. Okay, I didn't see Doug Scoville on my.
No.
Okay. So we don't have member count. I know we've got to be something functioning about 2 cameras. I think we had several new ones. I think we're 206 and Jeff is not.
No.
So I think, did I miss something? I think that was it. Anybody got anything else?
There's more pizza out there.
Yeah.
Grab some on the way over to Sherzer. You're welcome. No
Yeah.
problem. Always nice to have you guys over.
Some cookies out of the bus that we attempt to take home. That's ourselves up with.
But it's always a great thing to come and see your place.
Yes.
Yeah.
Great stuff.
Well, thank you.
Always.
Yeah, now next year when I go to the moon, I'll let you know. When So, anyways. Yeah, well, no, Boeing. Get stranded there.
Going from where you want to stay for a long time.
Yeah, right.
They're still up there, aren't they?
Yes.
Yeah, they are.
Yeah, sadly.
Yeah. Yes, sir. Or, anybody calls? Okay. Thank you.
For those online, we're signing off here.
So grab some more
Thanks for
food and
attending.
hold the